All right, today we are continuing our study of thermodynamics by looking at heat transfer, and we're going to look at it in terms of conduction, convection, and radiation. So, let's just jump right into it. Heat transfer is the movement of heat from one object to another. I'll write that down. Before we look at this, we look at heat as a type of energy. Now, if I had two objects, mass 1 and mass 2, and mass 1 had some kinetic energy. It was moving. When mass 1 runs into mass 2, after the collision, each object's going to have some energy. In this thing, because of the collision, mass 1 transferred energy to mass 2. That was an energy transfer. What we're looking at now is a heat transfer. So instead of looking at single objects, we're going to look at the particles in a whole lot of objects. So let's say we have object 1. Object 1 has a heat that's equal to, let's say, 200 joules and a temperature of, in Kelvin, let's say 400 Kelvin. And then we've got object 2. Let's say object 2 is a whole lot more massive. There are a whole lot more particles in it. So object 2 has a total heat of something like 1,000 joules. But the temperature of object 2 is only about 100 Kelvin. Now, we're going to talk about what each of these things mean. Heat is just telling me about the total energy. Looking at just the heat is not going to tell you how heat is going to move. Even though this has 1,000 joules of heat, it's not going to go from this object, it's not going to go from object 2 to object 1. We have to look at temperature to see how we're going to transfer energy from one object to another. This is essentially telling me about the kinetic energy of the particles. When I bring these two objects together, the particles in 2 don't have a lot of kinetic energy. They're kind of moving around, but they're chilling out. They only have, it's a temperature of 100 degrees Kelvin. They're not moving very fast. Object 1, there may not be as many particles in it, but they have a higher temperature. So the average kinetic energy of each particle is a whole lot higher than the average kinetic energy of each particle in object 2. So when I bring these together, we look at a zoomed in view of 1 and 2. When they're touching each other, their particles have the opportunity for object 1, the particles in object 1, which are fast moving, to run into the slower moving particles in object 2. Now, after the collision, they're going to share some of that kinetic energy. And we see overall in that collision that energy, the net energy flow was from object 1 into object 2. Through all of these collisions, kinetic energy of each particle in object 1 is going to transfer to object 2 until their temperatures are equal to each other. At this point, there's not going to be any more transfer of heat. That's called thermal equilibrium. Okay? the particles here can't give any more heat to the particles over here because they all, on average, have the same kinetic energy. Now, the total heat of object 1 may still be less than the total heat of object 2, but the average kinetic energy of the particles is about the same. They're not going to be transferring energy like this anymore. And that's the basics behind heat transfer. Now, conduction. You've talked about conduction a whole lot. In conduction, okay, we have transfer of heat by direct contact. Two objects have got to be touching for conduction to happen. That's how it works. Now, with conduction, with direct transfer of heat by contact, particles of substance 1, this would be a high temp, transfer energy to the second substance with a lower temperature until those temperatures are equal. The whole goal of heat transfer is to have equal temperatures. Conduction does it by touching, and the particles in each substance are the things that are carrying heat. That's important. Anytime we carry heat, something has got to do it. So conduction is particles literally hit. That's what we saw in the last slide when we were talking about heat transfer. Conduction's easy. If you're touching, you've got conduction. Convection is a little bit different to look at. So imagine we have a beaker, and that beaker is full of water. And we put a fire under that beaker. Now, the fire's touching the bottom of the thing, so there's obviously some conduction there. But what's going to happen is that by conduction, the bottom part of the water gets hot. And compared to that, the top part of the water is cold. Because these things are getting hot, though, they expand in volume. Think back to our discussion of BV equals nRT. If I increase the temperature, I'm going to increase the volume. It's going to make these things want to float up to the top. So we have hot particles moving to the top, displacing cold particles that come down. That thing is called a convection current. The important thing to note about convection is that a substance, and really we only see convection in fluids, that means liquids or gases, FLIDS, fluids, that substance heats itself and nothing else. If I were to take a piece of broccoli and stick it into the boiling water, the broccoli would get hot not by convection but by conduction, because it's touching hot water. There's direct contact between the broccoli and the water. Convection is occurring in the water, where the water heats itself. Air currents that are convected happen when the air heats itself. The air close to the surface gets hot and it rises, and the cold air falls. That's air heating itself. Convection is the substance heating itself through these convection currents. Radiation. Radiation is a little bit different. I guess the thing that we always look at with radiation is the sun. So on a warm day, you sit outside, and today your block happens to be black. And you get hot just from being out in the sun. Now, in radiation, you have photons carrying energy from sun to object. When the photon hits a particle in the object, so here's a photon, it's coming in. When it hits that, it's going to give it energy, and it's going to make that object move around a little bit more. That photon is transferring energy from the sun to the object. Now, what's unique about radiation is that there is no contact. This is heating through light. There's no contact and there's no current. There's no hot rises, cold falls thing going on. We have light making the particles in something move faster. Most of the time that's going to be from the sun, but in your microwave you use radiation. It's a different kind of photon. It's a light that you can't see that makes the particles in something move faster and faster and faster. Fast food restaurants use heat lamps. If you go tanning, you are baking your skin through radiation. That's how it works. So that's our heat transfer.